Ladies and gentlemen, let's look at the second way to handle heteroskedasticity. That one is quite easy, I won't lie to you. It is using the robust standard errors. Okay, the robust standard error. Sometimes it has a very long name. Please, when we use a long name, don't get scared. Okay, the robust standard error. Sometimes it's known as white robust standard error. Sometimes it's also known as heteroskedastic robust standard errors. Don't worry. And it is correcting for the heteroskedasticity. Sometimes, and many a times actually, you want to correct for both the heteroskedasticity and the autocorrelation. You correct them at the same time. In that case, you will use a certain standard error. It's a very long one. It is known as the Newey West robust standard error. But one way to solve the heteroskedasticity problem is using the white heteroskedastic corrected robust standard errors. I told you there are different strange names for it, but you don't have to worry. It was pioneered by White in 1980. It can be performed so that as we get bigger sample size, okay, inferences can be made about the true parameter values. So what this is important is that you are not going to change the coefficient. The coefficient will never change. The standard errors will change. The standard errors will change. Now, what I mean by this is this, and I want to take you back here. Okay. What I mean is that if you look here, okay, in the data set, you see, we have the estimate divided by the standard error, and every number you see, every estimate you see divided by the standard error will give you the t-value. Okay, it will give you the t-statistic. Every one of them will give you the t-statistic. Okay. And so what we are saying is that the robust standard error, it does not change the estimate, it changes the standard error. And once it's changed the standard error, the t-value, the t-statistic will also what? Change, because you divide the estimate by the standard error. So the t-statistic will change. And it is from the t-statistic you derive the p-value. And so the p-value will change. And so the significance will change. All right. So now that has been found to be very practical. I won't lie to you, the robust standard errors. Okay. The standard errors are larger than the normal OLS standard errors, which will lead to smaller p-values. And at the end of the day, what we want are what? Smaller p-values. That's what we want. Smaller p-values. But I need to sound a bit of a caution here. Okay. And the caution is that, technically speaking, in practice, we often don't test for heteroskedasticity. You know, I've done some tests of them. I've done several tests. And then one of you was even worried about, why am I doing so many tests and all of that? In practice, we don't normally do all of these tests. I don't like you. But what we do is that we directly report the heteroskedastic standard errors, so that it will imply that we've corrected it if it is there at all. If it is there at all, we have corrected it. So that is one thing you will note. I spoke to you that when there is a problem of both heteroskedasticity and autocorrelation, we use the Newey West standard errors. We'll talk about this later, okay? But strictly speaking, okay, it is valid when the sample size are large. If you have only 15 to 20 observations, the sample size is small, so you don't need this Newey West. But if you have 50 or more, the Newey West standard error, Newey West standard error may be useful in that regard, and that it might make it much more robust. Okay, so those are the ways. The second way of handling, so you don't have to change log like the transformations that we did. So we are going to apply that approach right here, that remedial measure here, and then you are going to see the result. So let's go to our R and then apply it. So the first thing we are going to do is this. We are going to invoke a command called library foreign. Our LM test, you remember we did it, and it shows that it's heteroskedastic. Then we invoke a command called sandwich. We'll load all of this. Okay, we'll load all of this. So this is under the assumption that you've not done it before, but you are doing it first time. That's what you do. And then we are going to use this command, coefficient gene multi. Okay, coefficient gene multi vcov, the variance covariance matrix of the heteroscedastic standard errors, the vcovH. The type that we are going to use is called HC, and later on you see that there are HC0, HC1, HC. These are different kinds of the standard errors that we tend to use, and this is the white standard error, also called Eicher-Huber-White standard robust errors. So that is it. Now you can change the AC to AC1, which is another form of the white, the Eicher-Huber-White standard error. Okay, all right. So we are going to try that first. So let me just do that here with you. So I'm just going to take you back up here, and you will see that I'll have to invoke my library and all my other commands in there. And then once you are done, you just apply the white standard error test. Okay, now watch something. Once you do this, this is what happens. You can see here that we are still able to maintain our coefficient, the estimate. You remember they were negative as usual. Nothing has changed from the original. Nothing has changed. And that's what we indicated. It doesn't change the estimate, but it corrects the standard errors. So you can see that the standard errors now, the variables are significant. Almost every variable is significant now. It's only a matter of significant at what percent. And price is significant at 5%. So that's good. Okay. Price is significant. Lock urban wasn't significant at all. Now it's significant at 5%. The only thing that is not beautifully significant is the income. Okay, the income is now significant only at 10%. Okay, that's it. The income is significant at 10% now. But apart from that, every other thing is significant. Okay, that is a robust standard error. It's easy and it solves the problem quickly. Okay, now we're going to put all of this together and then we'll talk about them. Okay. And then that was type. The general type. You can use the HC1 type, another type. Okay. And normally some people like to try those differently. There's another type of robust standard error. And you can see that that one, it wasn't only M income, but also it made log urban significant only at this percent. But the key point is at least, there are significant values there. And if there were, and this is important, if there was a problem of heteroscedasticity and autocorrelation, without checking, without doing anything, this is a practical one I'm talking about. Without checking, without anything, you do the robust Newey standard error. So that's what I'm going to do now here. Robust Newey standard error. Nothing appears to show, but it is there. So you can run this portion alone. And when you run this portion alone, this is what happens. Now, this is interesting, okay, because everything is significant at 0.1%. All of them are significant at 0.1%. Every single one of them is significant at 0.1%. Now, if you look at the coefficient too are what it is. They are what it is. Now, if you could remember this coefficient, it might look like it's different. It's not different. Okay. And I will put all of them together, then you will appreciate it. You can see that it is minus 2.3. It's not minus, it's actually minus 23 because you have plus 1 there. So it's minus 23. Okay. So it's minus 23. Okay. It's 0.0. Yeah. And if you look at a religion Christian, the one here means that you have to move the decimals to 5. You have to bring them after 2 decimals, after the first decimal. So this one will be 15.55. This one will be 46.4, blah, blah, blah. Okay, so these numbers have not changed. That's the point I'm trying to say. That I'm trying to indicate that the estimates haven't changed, but the Newey West is powerful. The Newey West standard error is powerful because everything here is significant. It's significant. Significant at 0.1%, 0.1%, 0.1%. And so if I want them to be significant, okay, this is the one that will showcase it beautiful. And you have to indicate it. It's very powerful. I want you to know that this is powerful. This is critically powerful when it comes to correcting for heteroscedasticity and autocorrelation. It's green. It's pure gold in there. Okay. Now, I will try and put everything together and see if we can be able to, okay, I'm going to try and put everything together with this command. I will not use this command. In fact, for the first time, I'm going to use a new command, okay, and then I will now put that together for all of us to see, because I didn't do this. But I'm going to do that here for you to see when we now put everything together. There's a package called Stargazer, and I've mentioned it before. And so what I've done is that install Stargazer. This is Stargazer. Install it. And once you've installed the Stargazer, you will be able to handle and put all of the data together beautifully and handle them all very, very nicely. Okay, I'm going to do that. But before I do that, let me take you back to the Newey West. Okay, so this is a Newey West standard error command that I told you about. It is the best so far. That's the point I've put here. It's the best so far on the Brukutu data set that we have. It is the best so far. Okay, it uses something called a Bartlett kernel with a non-parametric bandwidth selection. These things you just say them when you are actually writing a journal paper, just to indicate that you know what you're talking about. Other than that, you can go and read them. Okay, the paper was published in 87 and 94, just to understand. But this is a very, very good solution because it's giving us very beautiful, significant results there. So I want to take you back to our result, and now we're going to produce a very cute table with Stargazer. Okay, very cute table with Stargazer. Okay, I will do that with my next one, and then I will explain.